Okay, so we're going to go ahead and get started. So this is workshop number 2, ostensibly titled Dual Beam FIB Tips, Tricks, and Other Useful Info. I am recording this, so if you do not want to be recorded or you have any issues with that, now is your time to please vacate the Zoom meeting, and I will be happy to put a post up on the instrument page after this is done for you to view it. So I do have a preset set of topics here, but before I go into anything, because I'm obviously doing this for you guys, so if there's any specific things that you want me to address before I start addressing anything, I would be happy to do that. So floor is kind of open just initially if there's something somebody wants to ask about. All right. Wait till the sample gets to 4 millimeters and then, okay, we'll stop. All right. Well, okay, if you stop me at any point, just say, hey, I got a question, or something came into my head. Otherwise, I got just basic topics here I'm going to go through. So these kind of came to me during the week at different points. I've been carrying around just a scrap of paper here, just as thoughts coming into my head about, hey, I should cover this. First thing I want to touch on, okay, and I'm going to look like a giant hypocrite here. So is sample mounting. Is please, if it's all possible, is use conductive paint that is well dried. Okay, just for stability purposes in the microscope. If you're trying to do really accurate milling, you don't want your sample kind of creeping on you, moving around. If you use conductive tape, the tape is kind of spongy and it tends to be a little more problematic in terms of just the sample moving around on you. If you use conductive paint and it's well dried, it dries very rigidly, and that's really not a problem. So, and of course, I'm being a giant hypocrite here because the sample that's in here right now is, as you can see in the NavCam photo, and this is a little hard to see. Let me mag in on this so you can, right here, this guy, you can see. So this is what we're looking at here today. This is just a, it's a microchip or a microelectronic device, but this is actually mounted on carbon tape. So hypocrite that I am. This was a long time ago. So, but anyways, okay, so that's the first PSA, of course, is please try to use conductive paint. Now, I will say what you don't want to do is use conductive paint and then immediately put it into the chamber. You do need to give it enough time to dry. Usually you can plan that out enough and give it ample time to dry. Ideally, the longer the better. I wouldn't put it in and then or put it on and then immediately put it in the chamber. It's probably not going to be stable enough, and then you're going to have problems because your paint is still somewhat liquidy, and obviously that's not good either. So of course, give it enough time to dry. So all right, so aside from that, go here, head here, and we'll wake everything up. Okay, so the FIB, of course, we say the term FIB, but you have to remember the FIB is a dual beam instrument. It is an SEM and it is a FIB, although we pretty much always just refer to it by the FIB moniker. But the electron beam on the system doesn't usually get kind of the notoriety and kind of love and respect that it deserves. So I do want to spend some time kind of demonstrating some of the the functionality of the electron beam, because this actually is the electron column on this plasma FIB, and This is very similar to the one on the gallium FIB, just FYI. They're slightly different, but essentially they're kind of basically interchangeable. But the electron column on this microscope is actually probably the most advanced electron column of any kind of SEM that the university has in its possession. So if you're looking to do just some high resolution SEM work, this would certainly be, the system to do it in. All right, so I already have a voltage picked out here. So really quickly here, go ahead and focus, hit the UFO question mark button. Okay, we're pretty close to eccentric, but not quite. So we'll go ahead here and do a quick mechanical set to eccentric. Okay, that's pretty good here. Okay, so when we normally operate the system, we're usually using what's called field-free mode. So the electron beam on this microscope, it can operate in basically two modes. One's called field-free, which is kind of the standard mode, and then there's another mode which is called immersion. So next to the link working distance to the stage button, which again is, it's the UFO with question mark usually, you'll see there's another UFO button right here, but you have either one UFO or two UFOs. Okay, so the difference between these is what's called field free, or AKA mode 1, and immersion, which is mode 2. Okay, so immersion mode, I like to think of it as like high definition TV versus kind of like standard definition TV. Okay, so we'll just kind of see the difference here. Before we do that, let's go ahead and just align things in field free mode. So depending on the mode you're in, your alignments are always going to, be dependent on that. Okay, so for instance, if we align the system in immersion mode at 2 kV, 50 picoamps, if we switch to immersion, we're going to have to redo everything right down to, the crossover. So we can start with a crossover. All right, so that's pretty good. And we'll do the lens alignment here. Now, this is one of the quirks here, is that it doesn't start, the modulation is kind of low. So I like to put this amplitude somewhere around 0.5 or 50%. But again, this is a matter of preference. When you're doing this lens align, it's usually beneficial to keep your dwell time kind of short so you can see the shifting. So if I put the dwell time up higher here, right, I can't really see any shifting in the picture. So you need this, if you're using the full frame at least, okay, you need this down, I like around 300 nanoseconds. If you go to the reduced area scan here, depending on the size of the scan, sometimes you can bump up the dwell and still see the shifting. So this is actually pretty good here. I'm up to a microsecond, but I can still kind of see the shifting. So I'll actually go with this here. But you need the frame time, in essence, to be enough or fast enough that you get essentially like a live response. Okay, so it looks like we have mostly, the lens is okay. So we need to just do the astigmatism now. Okay. All right, now before we switch into high definition mode or immersion mode, a few things to address here. So we're all probably familiar with the black and white cookie here, the auto contrast brightness. And this is a very useful functionality, certainly, to do this. But sometimes this this doesn't work necessarily optimally, or sometimes it's a little haphazard. My understanding when you do this is what it's doing is it's looking at the histogram of the image, and then it's adjusting the contrast and brightness to do what's called a histogram stretch. So I can actually show you that really quick here. So and again, we're getting into some additional functionality, which is the point. So if I have this SEM image here, if I go to the eyeball, down here, you can see a histogram of the image. Okay, so histogram is grayscale value on the x-axis, and then the y is number of pixels. Okay, so this would be like peak white, and this would be peak black here. So what you want in a properly adjusted image is literally what you're seeing here, where the histogram basically expands the full, what's called dynamic range of the detector. Okay, so what you wouldn't want, for instance, I'll show you here. Okay, so see, this is not ideal, right? Because now I don't have the full range being used, and you can see in the actual image that I've lost a lot of the detail as a result of that. So this is another way you can manually do this adjustment. Okay, is you can actually look at the histogram of the image, then just go to your contrast and brightness controls, and then adjust accordingly. So the contrast knob, as a general rule, will tend to sort of expand or stretch out the histogram. The brightness tends to just shift it either to the left or the right. Okay, so that kind of gives you an idea what to sort of expect. Okay, and you can see here I can manually get back to kind of what the automatic system was doing. This can be a little bit dependent on the dwell time. So you can see as I or rather increase the dwell time, right, I have better signal to noise. Okay, and you can see now in this case, I could probably make some additional adjustments here, which I will do, and expand and get a little bit better dynamic range. So something like that, for instance. Okay. The other way you can do this as well is you can look at the actual detector signal as it's going across your image. So right up here next to the dwell time control is what's called the video scope. Okay, it's this little green line here. So if you click on it, this is what you see. Now there seems to be a little bit of a display glitch because of how I am sending the signal from the PC into my computer and recording it. So you can see here, there's a dotted line up here, a yellow line, there's one right here, and there should be another one down here that it's not showing. So actually, let me see here if, okay, so if I switch the zoom, then you can see it here. Okay, so just temporarily we can leave it like this. So anyway, this bottom line here, this would be peak black, right? And this top line is peak white. So what you want is this yellow line here, which is the signal, basically expanded to fill this whole range without actually hitting either of these extremes. Okay, so again, this is pretty good use of the dynamic range. So if I was to do this incorrectly, see here, you can see now, right, I'm actually exceeding the dynamic range, and now I've got saturation in the picture. If I turn off the scope, okay, so that's not very good, right? You're actually losing detail here because you have detector saturation. Some people actually, I've heard a few people say, when I'm sitting with them and I'm doing training, when I say things like you're saturated, that's what I mean is you have parts in the image where you're exceeding or you've hit peak white. That's what I mean by saturation. Okay, so again, I'm just turning down the contrast. I could do the same thing by just hitting the brightness and just turning that all the way up. Okay, so adjusting the brightness and the contrast The contrast you can think of as like the amplitude of the wave. Okay, so the contrast acts more to sort of expand the amplitude, not so much as a shift up and down, although it does do that somewhat. But the brightness is pretty much only a shift up or shift down kind of thing, like I'm doing here. So you can see the same thing if I go and I bottom it out, right? I end up losing detail as well. Okay. Again, this is somewhat dwell time specific. So if I go to a quicker dwell time here, I end up with more noise. Okay, my signal to noise is not as good. So this isn't really quite as accurate a representation as if I go to something more typical when I would actually do an image acquisition. Okay, so actually let me switch back here to zoom 80% so we can actually see all of this. All right, let me turn off the scope. Okay, and then let me really quickly here. All right, so let's go ahead and do an acquire. So now we've talked about in the training. So we have two cameras here. We have a snapshot. Okay, so these are presets here. Okay, that are basically like a lower pixel resolution and a higher pixel resolution. Okay, so you can see that's a pretty quick frame, right? I think that was, is that a 5 microsecond dwell time? Let's see what it says. Yep, it was 3. Okay, watch right here. Okay, so 3 microseconds. Okay, if I do the snapshot or the photo, so this is defaulted to 4 times the pixels and a 10 microsecond dwell. And so you can see we're getting a nice, not noisy picture. Okay, I'm not going to save this. Or actually, let me, I'm going to put it down here for the moment, actually. Here's another trick, right? If you want to put the E-beam in another quad, you can. Just come down here, click E-beam. Unpause it. So you could have 4 E-beams if you want. But I'm gonna record the image here and we'll compare high res mode versus low res mode here, or I should say immersion versus field free. And I'll just leave it there. All right. Now let's say, for instance, if you want to change these presets, for instance, you can. Okay, so these are obviously, this is something that I put in the software, so I'm not going to show you how to like fudge the preset permanently, but if you just want to do this kind of off the cuff, you can. So if you're doing photo here, let's say you want a different dwell time. Okay, just pick one from it while it's doing the acquisition, just put it on 5, and then it's going to reacquire it with the different dwell time. Okay, same thing here. Let me go back to 10. Okay, if you want to change the pixel density, you can do the same thing. Okay, so if you want to change this, just change it to a lower one, you can. That won't actually permanently change the preset, but then when it's done, it should, I believe, it should still prompt us to save as. Will it do that? Yes. Okay, it'll still do the same thing. Okay. Also, be careful with this button right here where it says save image with overlay graphics. So if you have this center cross in there, that will get burned into the picture. Okay, so generally you probably want to keep this off, or you want to turn off this cross, which I'll show you how to do now. So this cross is not there permanently. You can always get rid of it. Just come to view and then center cross, and that will go away. And then if you want to save with other overlays on here, you can do that. Okay, let me put it back on here for now. All right, so we're in low definition TV mode. So let's switch to high definition TV mode, AKA immersion mode. Okay. Now we have a pretty a longer dwell time right now. I do have some presets for the scanning. if you come up here, so up here on the upper right, where you have these S1, 2, 3, 4, 5, 6, these are scanning presets. Okay, so if you click this S1, that just goes to like a low pixel density and a fast dwell time. Okay, so you can see it's about, what is that, 0.13 seconds for the frame. Okay, so if I put this up here, okay, if I want to go back, just all I have to do is hit S1. Okay, that'll take me back to a fast dwell time. Okay, so you can always, if you fudge with this and you want to get it back, just hit S1. Okay, that'll take you back to the baseline. So anyway, let's start. So I just got to focus, go back to direct adjustments. Okay, and it looks like the crossover is still okay. Sometimes when you switch crossover or switch modes, your crossover will need to be adjusted. Looked like in this case, we were not really an issue. Okay. So the lens alignment's probably off a little bit here. All right, it looks okay. It looks like it's just astigmatism kind of left here. There we go. Excuse me. All right, so that's the same mag, same area. Let me go ahead here and I'll get our detector. All right, let's do a photo here. So hopefully that's pretty obvious, just looking between, you know, the immersion mode image and the free field or field free. I'm sorry, I confuse that all the time. I kept saying that for like 2 years. I kept saying free field for you know, the longest time, and then I finally realized, it's actually field free. So anyways, but we can see the difference here, right, pretty clearly between high definition TV and, you know, standard definition, right? So this works great for taking some really nice SEM images. So a few caveats with this though, with immersion mode. So the first is, let me mag out here. Okay, this is as far out as I can go in terms of the mag. So that's about, yeah, 1 1/4, or no, sorry, not 1 1/4. It's a little more than 100 microns field of view. Okay, so you're a bit limited in immersion in terms of how low you can go with your magnification. So this is definitely something that's meant more for the high magnification imaging regime. Okay. Another thing to keep in mind as well. Okay, let's say I pause this here. Okay, and I don't have anything set here, but you can also not live image in immersion mode while you are ion beam imaging or patterning. Okay, so we've actually seen this. Those of you, that's actually all of you, of course, who I've trained to operate this tool, how we can live e-beam image while we're ion beam imaging. And that's actually a constraint of immersion mode, is we don't have that functionality. Okay. What we would have to do instead is we'd have to take just intermittent snapshots while we are ion beam patterning. So, and actually, I will we'll show you that as well here in a moment. Some other stuff with immersion mode here. If I go into the eyeball, so I can actually change to what's called a backscattered only mode. if you do this in immersion mode, your alignment, not really with the crossover per se, but usually the lens alignment and the stigmation will need to be tweaked again. So let's take a look here. Yeah, so you can see the lens alignment is a little bit off. So the detector, when you're in immersion mode, it uses what's called a through lens detector. Okay, so you can imagine, right? Because you're adjusting that detector when you're changing the modes, can affect your alignment if you're changing how it's biased or how it's set. There's another thing here I'm going to point out in a second. Okay, so I'm adjusting the stigmators right now. One of the things you can maybe see here, let me do this to see how the image is kind of moving, right, as I do this. There's actually an alignment you can do for that. I'll show you here in a second. Okay. Okay, so those of you who have used the test scan, right, you're aware that the test scan, of course, has a dedicated backscatter detector. We don't have one of those on this microscope, but we can still perform dedicated backscattered imaging using the through lens detector. You could do this in field free mode as well, but I think it works a little bit better actually in immersion mode. Okay, so that looks pretty good right there. So that's your backscatter only image. And the other thing I was going to show you here was the stigmator centering. Oops. All right, we'll bump this back up here. Okay, so if that's not terribly bad right now, okay, but if you, I do have the center cross. If the image is shifting a lot when you're stigmating, what you can do is you can do what's called the stigmator centering. Okay, so again, I'm in direct adjustments here. I'm clicking the stigmator centering tab, turn on modulator X. You click on amplitude, just put in 50% here, 0.5. Okay, so now you can see the image here is moving up and down. Okay, so that means my stigmator for the X is not quite balanced. So again, I can use the crosshairs here just to see now it's worse. Okay, I can just use that to get rid of the movement. This, of course, is very strongly dependent on the voltage you're operating at. It can also be dependent pretty strongly on the working distance you're operating at. Since we do most of the work here at eucentric, which is approximately 4 millimeters, then we tend to kind of base everything on that. Okay, let's see, there we go. So now, if I want to adjust my stigmators, right, I'm adjusting it, my image isn't going anywhere. Okay, so that's just another little tool in the toolbox that you, the user, can adjust yourself if you feel so inclined. And there are some supervisor alignments that we can do that kind of get those in the ballpark, but that is something that you also have some control over as well. All right, let me take a look here in my list. All right, real quick here. We're 15. Take a look at my histogram. All right, so I need to turn the brightness down a little. I'm a little too peak whited. When you start to see, if you're using the histogram method, what you don't want to see is a pileup at either end, right? This is bad. Okay, you have a pileup of pixels at peak black. And then you can see here, if I go the other way, right? You got to pile up on the other end. Okay, so you're trying to avoid that. It's better, at least in my opinion, it's better to be sort of under, what's the word? It's better to sort of maybe not use the full dynamic range as opposed to be like saturated or have the signal clipped. So if we were to sort of verbalize that, so we just, okay, so we can see right here, I'm not using like the full dynamic range, okay? But this is much more preferred than say something like this, where maybe I'm using more of the range, but I have the signal kind of clipped, okay? And the reason for that, which I'll show you here, is there's another trick we can do. All right, so let's say, for instance, I'm going to record this image here, okay? Clearly, I'm not using the full dynamic range of the detector. The nice thing, though, is we can do an adjustment to this post-processing and basically digitally enhance this so it looks like we've used the full dynamic range, okay? So again, we're still in the eyeball module here, okay? So what we can do here is we can adjust the digital and the digital contrast as well as the brightness, okay? So now I believe what we want to do here, whoops. Okay, so basically, if I'm looking at this line here, I want this line basically going from right here on the left side of the curve, starting there, and basically terminating at the other side right above there. Okay, so this is pretty close right here. Okay, so you can see what happens here. If I'm adjusting the brightness down, I'm moving my pixels, you know, to the right or to the left, I'm sorry. And if I'm going the other way, I'm moving them to the right. Okay, if I do digital contrast, that's changing the slope of this line. Okay, so you use a combination of those things. Something about like that. That's pretty close right there. Okay, and so I can get an enhancement to the picture. Okay, so let me turn it off here. Right, that was the original. Okay, so you can see I was able to squeeze a little more juice out using a digital processing that I couldn't have gotten otherwise. Okay, again, just another tool for you to work with. And is there, see, there is an auto levels here. So let's actually take a look at that. We do this here and we do auto levels. Yeah, so that does basically the same thing. It's attempting to stretch and basically, you know, fill the whole histogram. Okay. And if you want to get rid of it, just you hit default, that goes back to normal. All right. This, of course, is done for the electron beam, but you could do the same thing for the ion beam. No problem at all. So the same basic principle applies. Obviously, with the ion beam, we don't have immersion mode, and we're only using the ETD, I believe, while we are performing ion beam imaging. So I think that was what I wanted to cover with immersion mode. A couple other things here. So let's say, for instance, that you have a setting here with your electron beam that you really like. Okay, so let's say you're taking this image and you really like 5 microseconds and 768 by 512. Okay, what you can do here, if you don't want to go through the hassle of setting this up each time, you can go to File here, Export Scanning Presets. Okay, so what this does is it saves these. So if I go to my If I can find it. There it is. Okay. Save these in your folder, right? In your on your shared data, okay? And then when you want them back, just go to import, scanning presets, go ahead and find them. They will load automatically. You can recall them instantly. You can do this with lots of other stuff too. Okay, you can do this with patterns, which we'll kind of get into next. So let me switch back to single UFO mode here. Actually, before we do that, I'm going to put the TLD back to secondary plus, excuse me, secondary plus backscattered. It should say secondary plus backscattered. There is no such thing as secondary only mode. But you can see, right, I switched the TLD mode and my image is now blurry. So, all right, back to field free. All right, and I'm gonna go ahead and just give myself a little bit more current here. If you switch electron beam settings and you can't find your beam, it looks like we're pretty close actually. Oop, that's not good. Where'd all my signal go? See, that's UC mode. Something might be a little bit, that looks okay right there. So there might be something going on with these middle ones, but okay, we'll leave it here. Anytime you fudge with any of the beam parameters, your alignment's probably going to get thrown off and you're going to need to just retweak it. Hit S1 here again. The one thing I would like to point out, in free field mode, specifically and at low kilovolts with the higher currents, this is something I've noticed on this microscope, is there tends to be a little bit of astigmatism that I can't end up getting out. And I think what that is the result of is probably a little bit of contamination inside the electron beam column. And the reason that, of course, is probably occurring is because we often use those crazy high currents with the PFIB beam. And of course, all that stuff has to go somewhere. So some of it, invariably ends up getting sucked into the electron column. So that would make sense that there's probably maybe a little bit of contamination in there that maybe is causing that. I don't really see it in immersion mode or at the lower currents, but I do tend to see it at these higher currents at low voltage. But anyways, okay. So let me go ahead here. We'll tilt to 52 degrees. See, I wonder if I got a little bit of settling with the sample because I was using tape, right, and not paint. So, all right. What do we have here? We have a nanoamp. Let's drop this down to just 30 picoamps here. There we go. All right, there's our live ion beam image. Okay, so a few little tips I wanted to go over with the ion beam here. Go ahead and freeze it here. Okay, so you have to remember always while you're using the ion beam, you're blasting and you're blasting your sample and removing material and potentially damaging it and losing protection. So you have to keep that in mind. Obviously, when you're down here in tens of picoamps, that's a very slow process and it's not so much of an issue. But when you're getting up in here, then it's really easy to just kind of blow through everything pretty quickly. Okay. So just some kind of general tips here. If you need to do some focusing at like a high current, for instance, okay, one of the things you can do is, and in this case, well, let me really quickly here. I'm going to swap here, go to a nanoamp really quick. Okay, so again, I'm manually adjusting, right? You can see the scope here for the ion beam image just as well, but all right, so let me go ahead here. And I am going to draw an X. 45 degrees. Some other stuff you can do here, you can position your patterns anywhere. I mean, you can obviously click and drag, right? But let's say I want to put it dead center in the picture. I can actually just say 0. Whoops. Oh, look what it's doing, actually. That's pretty neat. Will it let me do this? Yep, there we go. So then if I do, look at that. Okay. All right, so let me copy this guy, paste. And then I'm going to go back to oops. Negative 45. There we go. Okay, perfect. So now I've got a perfect overlapping X here. I'm going to move this right here into the corner. What's my depth? We're going to go deeper than that. Okay. Are they both 10? Yep. Okay. All right. Set our pattern to parallel here. Go ahead and just burn us an X. Let's take a look here and see what we got going. Okay. So the reason I'm burning an X here is so we have a nice recognizable feature here for what I want to show you next. Actually, I'm going to use that to demonstrate a couple other things. So every time you execute a pattern, it'll come down here. You'll see this green bar while it's in progress. Okay, so it'll show you things like how long it's been going, how much time is left, and so on and so forth. If you exit out, it just goes back here. That's good enough, though. I'll stop this now. All right. So let's say we want to use this X again here. Okay. I do have right here where it says P1 through 6. These are presets. There's only 6 of them, unfortunately, for patterns, but we can still do the same thing here. Okay. So if I do Control All, I can go to File, Export Patterns, and do the same thing. So if you have a special pattern that you like, that you use frequently, that you don't want to keep redrawing every time, you can do this. So it's called My Pattern File. All right, so we'll just call it, Test X. All right, so if I delete these, see if it works. And there we go. All right, perfect. So it does everything. Same, whatever application you set, if it's parallel or not, and it'll recall it immediately. Okay. So again, just another trick to maybe save you some time. All right, but now we have this X cut in here. Okay. Let me turn up. Now I can't really see the X that well. There we go. Whoops. Okay, there we go. Okay, so you can use this X now here, or you could use this with any sort of recognizable feature, but this works really well. If you need to do any focusing and stigmating, because let's say right here in the middle, you've got your sample or something of interest, okay? You can turn on reduced area, put it around your X, okay, and then unpause it, and now you're only, ablating this away, okay? So now you can focus. You want to adjust the astigmatism or correct the stigmators, you can, and now you're not doing this right on your sample, okay? Okay, so when you're done with this, what you don't want to do is uncheck this. If you do this, you're going to start blasting the whole area, okay? So what you want to do is hit the pause button. Hit the pause button, then unselect it, okay? And now you're good to go here. You can go back to a snapshot, okay? But that is just another trick here that you can use. So something that was going on here that I had to stop. This is kind of a good segue for this. Is using what's called spy mode. Okay, so actually, I'm going to pull up the X pattern again here, so we have something to look at. Okay, there we go. And we'll put it right here. All right. So those of you, is there anybody? I'm just curious here. So we've got, how many people are here? Oh, only 4, including me. But I don't think has anybody here used any other FIB besides like one of these brand new FIBs? Anybody use like a really old FIB besides me?
You don't mean also like the gallium FIB?
No, I mean older than that.
Okay, no.
No? Oh, okay. All right. Well, so originally when dual beam instruments came out, they didn't have the ability to live electron beam image while you were ion beam patterning. That was a more recent functionality, and it's a great functionality to have by all means. But the original instruments didn't have that. Okay, so what you had to do basically, if you wanted to monitor the milling progress, what you were forced to do was take snapshots intermittently while you were there. Okay, so basically every however long you wanted to, okay, you take a snapshot, right? Go a few seconds, take a snapshot. Go a few seconds, take a snapshot, right? You couldn't just unpause this and just watch it live, okay? So then obviously, the technology improved and an additional functionality was added. So obviously we got the functionality to live image while milling, but we also got the functionality, and this is really just a software thing, not really like a hardware thing, but we got the additional functionality for the system to just automatically take snapshots for you while you are patterning. Okay, so this is where you have what's called spy mode. Okay, so if you're in the patterning page here, okay, down here where it says I spy, okay, so you want to start. Obviously, we have our pattern set here. What we want to execute, we haven't executed it yet, but you want to click this on, okay, and then time interval. So what's going to happen here is every 5 seconds, this electron beam is going to refresh. Okay, so it's going to refresh using whatever dwell time and whatever pixel resolution is right here. Okay, every 5 seconds. Okay, so we can see this in action here. I'll start the pattern. And then over here, I just have to unpause this now. Okay. And it will do its thing. Okay, so see, every 5 seconds, right? It's taking a snapshot. So obviously you can, right? If I want a longer dwell time here, I can just do that. If I want more pixels, I can do that. I want less dwell time. If you want to change the time interval, so if we drop it down to say 3 seconds here, I believe you can even go like, many like fractions of a second. Okay, so if we wanted to do say a 2/10 of a second here, I believe that will work. Yep. Okay, so this saves you the hassle, right? If you don't want a live image, okay, while you're working, okay, you can set this up so that every so often it just automatically takes images for you. Okay, and that's called spy mode. One of the advantages of this actually, as opposed to doing the live image, of course, is the signal to noise. So if you take an actual snapshot, as opposed to using the live image, usually you can see a lot more detail than what you would see while you're patterning, because you have that interference that we've seen. So we can actually demonstrate this here. So if I want to go back to normal mode, just hit pause, turn this off, uncheck it here, and then just come back here. Okay, is this still going? It is. So we've got a nanoamp, and it's actually not too bad here. Yeah, I mean, we can see a little bit of interference here, but it's not terrible. We have a pretty favorable current ratio here. So again, if I was to make this, actually I can do that artificially here. So if I drop this down to say 50 picoamps. Okay, so now we can see I have way poorer signal to noise than I would if I was up at 0.8 nanoamps. You can do all these alignments while you are ion beam patterning. You can do the E-beam alignments. That is possible to do. Obviously here, this is really noisy. So it's kind of hard to do that, but anyways, actually, oh, let me go back. My bad. Okay, so let me go back here so we can see the spy mode in action here. Okay, so now, right, if I take the snapshots, okay, and this is pretty quick here. So, every 0.2 of a second, I'm taking a really short acquisition here. Okay, but this allows me to kind of, monitor the process. Just another way to do it, right? So just another tool in the toolbox. I like to use this when I'm final thinning a lamella and I'm trying to just get it so I've almost shaved off just that little bit of platinum left on the surface. So by doing this, I can really get that nice image and really see, that last few maybe tens of nanometers left on there. If you are using immersion mode, we know we can't live image while we're using immersion mode, but you can do this with the spy mode. I think though it's a little tricky to do that because like the brain of the system is sort of using a little bit more horsepower when it's doing immersion mode. So it's a little bit, the system tends to lag a little bit more if you're doing this while you're in immersion mode. So it tends to be a little easier on the system if you do this just in field free as opposed to immersion, but you could do this in immersion. If you you want to do this on the gallium fib, I have tried doing this in immersion mode on the gallium fib, and it is extremely slow. Just the response time of doing this is there's a lot of delays between taking the immersion mode image and then returning control to doing the pattern and then going back and forth. So it doesn't work, at least on the other instrument, extremely well when you're in immersion mode, although I haven't really tested it here. But since we're here right now, we might as well actually do that. Let me go ahead and pause it. And we'll see, just for starters here, how well this works in double UFO mode. There we go. All right, so the lens modulator may be off a little bit, but this is a little tricky to do on a slanted surface, but we'll do it anyway. Always better to do E-beam alignments, especially lens alignment on a flat surface if you can, but we didn't here. That's okay. All right. Ah, okay. This is a trickier one for the dynamic range because you've got, you know, pretty wide range here because you have this hole that we just cut, but that looks pretty good right there. All right. Let me go ahead and freeze this. Take a snapshot with the I-beam. I'll just place this guy. And we'll place it right here. All right, so let's put this at, we'll put it at 5 seconds here just to start. Okay, on pause. Let's see what we get here. Oh, this actually works pretty well. Yeah, when I did this with the, when I tested this with the gallium fib, this was really, really slow, but that's not unsurprising. That's a much older system. It's running on Windows XP. This is running on Windows 7, and plus it's about, I want to say it's 15 years a newer system, so that doesn't necessarily shock me. So we're down to 2 seconds per mil. There does seem to be a little bit of a lag, I would say, that we weren't seeing. Clearly, we're going more than 2 seconds here between screen grabs, but it's still reasonably fast. So, okay, so that's good to know. Go ahead and pause it here. Turn this off. So you can see, right, this is going here, but I can't unpause the image for the E-beam, right? Not allowed to start image acquisition. All right, let me go ahead and stop this. Okay. Check my eyeball here. Looking all right. All right, now one of the, let me see here. I'm gonna cut us a trench here really quick. Yeah, okay. All right, so I'm at 15 nanoamps, so I'm gonna use the reduced area trick here. Help focus. All right, go ahead and do that. I'm not gonna run this to completion, just enough here to. Actually, do I need to cut the other direction? Yeah, I do. Sorry, need to rotate this. Oh, that's right, actually. My bad. Okay, there we go. Okay, that's gonna be, just give that a couple minutes. I will be right back here. I'm just gonna go to the restroom. All right. And of course, you don't have to use spy mode. You can just, if you want, just periodically take snapshots, right? That's, perfectly fine as well. I'm gonna stop this in just a second here, right as that pass progress bar gets to the end. Okay, good. All right, so. Okay. I'm gonna acquire an image here, and then I'll show you some additional stuff we can do here. Okay, so some additional functionality that you have here is to actually take some measurements. Okay, so one of the questions that people ask me all the time are things like, well, how deep am I cutting into the material and so on and so forth. Obviously, when you have the patterns that you're running, you know, it has an input depth. The thing you have to remember, of course, is that you know, these are calibrated for certain materials. We're not cutting, I mean, the substrate on this is silicon, but it's got a bunch of layers into it. So, but I wouldn't necessarily, you know, say that when you put 10 microns in here, you're exactly getting 10 microns, you know, deep. So, but anyways, if we can see pretty clearly here though, right, this cut face here. Okay, so let's say we want to figure out how deep does this go down. Okay, how deep does this go down, right, until, see, it's cut off here by this lip, right? But how deep does this go to right here? Okay, how deep is it along this, you know, into the material? Okay, so I can actually do that right here with one of my handy dandy measuring tools. Okay, so if we do line measurement, now if you want to do a purely vertical or purely horizontal, if you hold shift, oh, wrong one, not shift, control. There you go. Okay, if you hold control, then that will constrain it to be perfectly vertical or perfectly horizontal. Okay, so then you can just click and drag just like this. Okay, and what it's saying is it's 7.5, a little bit more than that micrometers. But okay, you have to remember, we're looking at this at an angle. Okay, so this is not the actual distance along that cut face. Okay, so this ends up inside of the patterning tab here. But if you find where it says properties, what we have to do is we have to correct the measurement for what's called cross section. Okay, so down here where it says tilt correction, you find where it says correction, you click cross section, and you'll see now it's got a little CS on it, okay, to denote that it's a cross section, okay, and it's telling you that this depth is actually about 9.56 micrometers instead. Okay, so this will automatically figure this out depending on your stage tilt. It's not something you have to do yourself. Okay, this works great. So now if we were going this direction, it wouldn't matter. Okay, if we're going perfectly horizontal, right, you can see if I switch to none, the CS goes, but nothing changes, right, because I'm not tilted in that direction. Okay, but if I'm going vertically, it matters, or if I'm going at any sort of angle, it also matters. Okay, so you can see here if I want to know that distance along the cut face, right? Okay, that's not the same, okay, as if I do that. So you want to make sure you turn on where it says cross section correction. This is probably the most typical thing people want to know is like, how thick is the layer? How deep did I cut in? Things like that. Well, I'm telling you, this is how you can do it. Okay, so we can actually, if we constrain this. Now, if you want to save this image, you have the plus here. Let me turn off the plus really quick. Okay, if you want this in color, you want to save it as a 24-bit, okay, and then save with overlay graphics. That will save this as a color. If you save it as 16-bit, this will get saved as a grayscale. Okay, just FYI. All right, so we'll go ahead and just cancel that. There's lots of other measurements you can do as well. Usually the ones I use the most are just like rectangle or the line. So the rectangle will give you basically two directions, right? So give you up and down along the cut face, and then it'll give you, you know, wide. So this accomplishes kind of the same goal, just it's like two lines basically. All right, let me take a look here at my handy dandy list here. All right, so we talked about exporting presets, doing all that stuff. Okay, I want to make a couple mentions here about doing some work with the easy lift. or you're using, or you're extracting lamellas. Let me switch back to field free mode here. Back to single UFO. I'll hit S1 to get us back to the fast scan rate, and I'll go back up to 0.8. All right, so you're gonna have to do a little pretending with me here. So we're gonna have to pretend that we have a lamella in here that we're ready to extract, because clearly we don't, but we'll pretend that we do anyway. All right, so we'll go ahead and insert the easy lift. Right, and now before my easy lift is anywhere near where my, quote unquote lamella is, I'm gonna insert my platinum GIS. Okay, so every time you insert the platinum, there's a little bit of a mechanical vibration associated with that, and you want to try and be kind of cognizant of that when you're working with the easy lift or the Omni probe. If you're on the other microscope, that vibration, if done at the inopportune time, can cause you problems, can cause you sample loss, can cause welds to bust and things like that. So I'm actually going to go over with you here a few ways to hopefully not have that happen to you, because that is frustrating. All right, we'll switch to the easy lift, go down here. Though I will say that the vibrational issues that I'm going over here, they are far less on the PFIB than they are with the gallium fib. Again, that's just an issue of age of the system and how it was designed. You're talking about something 15 plus years newer that just has sort of more attention to detail. Okay. Get the easy lift nice and close here. Stop it on the plus. Okay, looks like we're smacking into the surface. We'll leave it there. Okay, so, and actually, to make sure I'm simulating this. All right, so let's say the lamella is down here. So I'm at least a good few microns away from the sample, okay? What you don't want to do here, let's say you're welding this. You want to weld the lamella to the easy lift here. What you don't want to do is get everything positioned, okay? And then tell it to weld. Okay, so where's the preset here? Right here, okay? Okay, what you want to do before you have that is, we already have the PT inserted. You need to open the flow or the valve to the GIS before you do that. So the reason you want to do that is there's another vibration associated with that, and that can be enough of a problem to maybe cause you maybe to lose the weld or the sample to break that last little point of attachment. So you have a little bit of room here, okay? And there really wasn't too bad of one on here, but I've seen this be really bad on the other system, okay? But you want this open first, then you can do the rest of the positioning. Oops. get it close. Okay, so right there, if we're saying that's close, okay, we can position this and then we can execute the weld. Okay, so we want to make sure we get all the possible, you know, quasi-traumatic vibrational occurrences out of the way until and then we can do the weld now. Okay. All right. So again, the flow process is put the easy lift in, put the GIS in, get the easy lift kind of close, not all the way there, then open the flow to the GIS, then approach it, and then all the way, and then do the weld. Another thing to point out here, and this is unique to the PFIB that we've seen, that you need to use a fairly high current density for doing the welds. Okay, so what I've discovered here personally is that you need to use about 10 times higher density than we would use for optimal just, you know, deposition, right? So I went to 300 picoamps and I have preset 4. Okay, so I sent out an email about this, but this gives you about a 100 picoamp per square micron current density, but it gives you, and so it's not optimal for growth of platinum, but it does a really good job of getting you a nice firm weld. Okay, so I've been using this actually not only for welding to the easy lifts, but actually for welding the lamellas to the grid. So again, I'm at 300 picoamps, and this is pattern preset number 4 here. Okay, again, if you're on the gallium fib, it's you know, it's not as critical. You could just use 30 picoamps, your kind of typical, just optimal growth beam current density. Okay, so we'll go back here. It's all because of that those xenon atoms. So those xenon atoms, they're pesky little buggers. They don't like to bond to things. They like to make bubbles and they like to sort of do their own thing. So whereas the gallium atoms, they like to, you know, kind of cozy up a little bit more, and they're a little bit more willing to kind of interact with the other things in a kind of a harmonious sort of fashion. Whereas the xenon just says, you know, I'm this snob gas and I want out of here. All right. Whoops. All right, let me take a look here at my list. All right, so we're about an hour and a half in here. So I've covered most of, pretty much all of what I wanted to cover here. Is there any, there's actually, well, there's a couple more things here I can do, or actually one more thing here I kind of wrote down. Let me take out the platinum here. All right, I'm going to draw a just regular cross section for the sake of argument here. All right. So a few things to point out with the patterns. So every time you draw a pattern, you have to give it an application. So this is basically telling it you're either removing material or you're depositing material. Those are really the only two things it'll do. And so in terms of material removal, we have three options here. So silicon, silicon carbide, and alumina. So the silicon, obviously, that's just kind of the general, catch-all one. If you're not sure what to use, just as a general file. But basically, this is calibrated assuming you're milling normal into a surface, like you're trying to remove like a cube. Okay, so inside of this file, there's information that tells it how much material it removes as a function of ion dose. Okay, so I think in the calculation it's something like volume. Is it volume per ion? I believe something like that. Okay, so based on that, and you can measure that. There's ways to do it. Okay, you can actually figure out for so much current, and this is how deep I want to cut. Right, how long is that going to take me? Okay, but the kind of more nuanced things in the file, okay, are what's called the overlap of the pattern. Okay, so this is kind of well, again, as I said, it's a bit more nuanced, but this is something that a lot of people don't necessarily pay attention to, and it's a little kind of more technical than I guess your typical run-of-the-mill user would probably look at. But so what is this parameter overlap? Okay, so let's say, for instance, just because the math works really well, let's say that I have a beam and my ion beam, and my ion beam diameter is 10 nanometers. Okay, so when I'm executing a pattern, it's digitizing this pattern and it's figuring out some spacing between beam points within the pattern. Okay, so basically the beam sits at a point for some amount of time, then it moves to the next point, then it moves to the next point, then it moves to the next point. Okay, so let's say, since my beam is 10 nanometers, okay, and let's just say for the sake of argument, my dwell time is a microsecond. Okay, so I'm going to dwell for a microsecond, and then let's say I move the beam to the right 10 nanometers. So now if you look at those beam profiles, right, they're just touching on the edge, but there's no overlap of the beam. Okay, and that would be what's called an overlap of 0, right? So basically my beam positions are separated by the size of the beam. Okay, that would be an overlap of 0. So let's say instead, right, I move the beam over by 5 nanometers. Well, in that case, right, I have overlap of the beam profiles in that case. Okay, so that would be, right, I'm separated by half of the beam diameter. That would be an overlap of 50%. Okay, so again, if I have a 10 nanometer beam and my beam spacings are 5 nanometers apart, right, that would be an overlap of 50%. Okay, hopefully everybody kind of follows, right, how this works. So inside each of these material files, there is an overlap parameter. Okay, the reason this is important is that it's useful to make sure that you end up with usually the smoothest mill. Okay, so you can imagine you would need some amount of overlap of the beam when you're doing this, or else you're probably not going to end up with a nice smooth cut face, right? You're going to end up with maybe a cut face that has ripples or corrugations in it. Okay, so we can actually show this here. I'm going to actually switch this. Let me switch to a rectangle. That's going to show it a little better. And we'll switch to silicon again. Let's do 10 by 5. And we'll just do 5. And so this is programmed as 85 as the default, but you can change this manually. Okay, just if you type in 0, it'll set it to 0. Okay, right? So what it's going to do here, where it has pitch, this is the spacing between beam points. Okay, it's going basically half of a micron between beam points. So again, if the overlap is 0, then basically this is saying that it's estimating the beam to be about half of a micron in diameter. I think that's in here somewhere. Is it in here? Yep, right here. Okay. So this is what it's estimating to be the beam size. So again, based on the voltage, based on the current, it's figuring out using some calculation what is the size of the beam. So that's what it's using to, when you tell it such and such an overlap, that's what it's using to figure out the beam spacing. Okay, but we've programmed this in to be 0. So let's go ahead and run this. And let's see what we get here. You can actually also have negative overlap, right? That would be where the beam is actually spaced farther apart, or the beam positions are spaced farther apart than the actual beam diameter. Okay. That does appear in a few instances, though not typically when you're doing things like milling. And I can't really tell here. But actually, no, we can kind of tell in the bottom here. This image is not the best one either. We might need to switch to a high definition mode to really see this. Where are we at here? I'll stop this at depth of 2 microns. All right, there we go. Just go back to 100 picoamps. Okay, lens alignment looks okay. All right, let me take a look here at my okay, so if you look here in the sidewall, I don't know how easy this is to see, but you can actually see there's a little bit of rippling going on here. Okay, so what I'm going to do here, let me switch here, actually, on pause. Let me do an acquire here. And then I'll do a digital adjustment to this as well to make it easier to see. But I can see these on the sidewall here. See right here. Okay, kind of going vertically. There we go. All right, so let me move over here. And let's change our overlap back to 85%. So now we've got a substantial amount of overlap. We'll do 2 microns again to make sure we're consistent. So you can also live ion image if you have like a rectangle or a regular cross section. You can do that here. Sometimes I've noticed, and on the gallium fib, this works pretty reliably. On the PFIB, I've noticed some issues with this, sometimes intermittently not working. So I mean, I clicked on this. Oops. I clicked on this, and then you unpause it. Then you can get the signal from in here. I'm just manually adjusting the contrast and brightness. Although sometimes I've seen where the knobs are unresponsive to this, but it seems to be working fine now, just like it should. So I won't complain. All right, so we're going to take a look at the sidewalls here and see if there's any difference. We're at 15,000. And this may not be the best material to do this with because it's got some surface corrugation. Well, maybe not corrugation already, but some surface roughening. So yeah, so you really can't see a huge difference here. Although you can, well, you know what you can see though, actually. Okay. If you look at the bottom of the trench, okay, you can see in the bottom how smooth this is here. You can actually see the ripples here in the one with the 0 overlap. Okay. Right. So I think that's a little more dramatic. With the sidewalls, it's a little hard to say because we're starting with a rough surface. Although I can see these from the beam path here. But yeah, if you look at the actual the bottom of the trench, so you can see kind of the ripples in there. Again, that's indicative of that bigger spacing than you would have had here. So anyways, you can feel free to play around with that if you want when you're doing, your own executions or your own patterns. As a general rule, you tend to be using higher overlap than when you have like a harder material. So if we have, for instance, I draw the rectangle here. So with silicon, I have it defaulted at 85. If I go to silicon carbide, it's bumped up a little bit. And then it's bumped up even more for alumina. With the gallium fib, what I've noticed empirically is you don't need as high of an overlap than you do with the PFIB to get like a smooth cut face. So that's another one of the sort of quirks between the two systems is there tends to be just more of a curtaining effect with the plasma fib than with the gallium fib. So, but yes, that's the sort of, what's the word? Rather important and yet not often understood or emphasized parameter known as overlap. So, but again, that is dependent on an assumption about the size of the beam, right? So it's assuming here that your beam diameter is this. So actually, if we go to, just to see here, what's it say the beam diameter is when we go to 100 picoamps? It says, that can't be right. Let me try drawing it again. Okay, so it did update it. So it went to 180 nanometers. Okay. And if we go to say 60 nanoamps, yeah, so it's saying it's about 1.6 micrometers. So that would actually be a good parameter to use in terms of maybe like spacing when you're, maybe like cutting trenches, right? So if the beam is estimated at 1.5 microns, you probably want to space your patterns maybe at least that far away from areas you're trying not to like overmill, for instance. So, okay. All right, so we are 1 hour and 45, 1 hour and 40 minutes in-ish. So that is all I had on my list here specifically. Is there anything else anybody would like to ask, like me to cover? Things in general. One thing with the nav cam, let me show this with it. This is kind of cool with the nav cam. So, I mean, like at this mag, you can't see this, okay? If you go to the eyeball menu, right? And if you're dealing with like a microelectronics, device or something, a small chip, you can do this. You go to the eyeball menu for the nav cam, right here where it says digital zoom, okay? You click the plus, right? Then you can get this green box here. You can drag it around, okay? But now you can go in pretty far here, and now I can see all, a lot of detail on this chip, okay? So I can actually move. So the green plus is telling me where I am on the nav cam photo right now. Okay, but this way, right, I can zoom in digitally pretty high. Okay, so if I want to go to say this corner of the chip, I could do that. Let's see how, yeah, so this is actually pretty accurate in terms of its position. Okay, so if I want to go up here, just double left click. If I wanted to go over to this other side, same thing. Okay, but that's just another way to sort of get the most out of the nav cam photo here. That's another way you can move. Okay, so this green thing here, this is showing you the view area in the SEM image. Okay, so you can actually see if I mag out, or in this case mag in, right? So this is right. I can see the area gets smaller. That's pretty neat. Okay, so I can drag this wherever I want. If I click and drag it here, it'll take it there. Or I can do the same thing here. So if this is hard to see, you can do digital fudging with this as well. Okay, so I can reset this. I can make it a little easy, same thing, adjust digital contrast, whatever, if I need to. And then you just mag all the way out, digital zoom, and there you go. So, all right, so that was the only thing I wanted to mention about the nav cam, because I do use that quite a bit. So any questions about anything?
I have a question.
Go right ahead.
For the through lens detector, I know we usually use the 4 millimeters anyway, but is there a height that it has to be at?
As far as
working distance, yeah.
No, that will work at any working distance you want.
Oh.
You could get it really close. If you wanted to do, some super close working distance stuff, you could. In fact, it'll usually work better at shorter working distances.
Okay. Like the other one.
Like the Nova, yep.
Yes, thank you.
Yep.
My brain's quit working for the day.
Exactly.
Okay.
So, yep.
Yep.
Yeah, those if any of you have used the Nova, I mean the immersion mode is very similar, although this one is actually spec'd as higher performance than the Nova one is, just to give you a shameless plug there. All right, any other questions? All right, well, let me go ahead here. I will stop the recording.